Welcome to this last session of ICNP 2020. Welcome especially to the speakers, and welcome to everybody who has come to attend this session. Maybe this is the thing, you can also attend the sessions. It's not the last one if you're not actually physically there, right? So let's see. So we have three very nice papers about wireless. I think they're very different from just pure protocol things. Let's start. So as I said, I don't know if everybody was already online. I will introduce the speaker, of course, and they have the talk, and then we do the Q&A here live. And if you want to ask questions, just raise your hand. And then turn on the camera while you are asking the question and while you are interacting with the speaker, so that this becomes a bit more lively and not so lonely. Okay, so let's start with CSIscan, learning CSI for efficient AP discovery in dense Wi-Fi networks. This is a talk by Kunal Sankhe, who is an engineer at Qualcomm, right? Doing your PhD in using deep learning for wireless, right? I didn't exchange you with anybody else. So, so go ahead, share your screen and present. You have 20 minutes and we'll go to the Q&A.
Sure. Thank you, Anna. So let me know if you can see my screen. Can you see my screen, Anna?
Yes, I can.
Okay, so I'll start. Hi, everyone. I'm Kunal Sankhe, and today I'll talk about our work, CSIscan, which is an efficient way of discovering access point in dense Wi-Fi network. So this is a joint work with my colleague Dheryta and my advisor, Professor Kaushik Chowdhury. This is the outline of my talk. So in today's world, we know that Wi-Fi is no longer a luxury. It is our common expectation to have a Wi-Fi connection. We use Wi-Fi not only at our home or offices, but also while shopping at shopping mall or at even subway station, or probably even at stadiums. Now imagine that you're walking inside the stadium and there is a Wi-Fi connection available. The first thing that you will do to access Wi-Fi is to search for all available access points. Now, this process of searching an access point is called AP discovery. Now, along with you, there are thousands of spectators who are trying to access, who are trying to find the access point. Now, this simple process of searching an access point causes a huge overhead on the Wi-Fi network. And therefore, this AP discovery is said to be an Achilles heel for Wi-Fi. And this is especially true for dense Wi-Fi network. Now, to provide real-world evidence of the problem which is caused by AP discovery, we conducted two studies. In the first study, we tried to analyze what is the spectrum wastage that happens because of the exchange of discovery packets. Now, for that, we collected Wi-Fi traces in our student cafeteria, where around 100 to 120 students were present, and they were accessing Wi-Fi using their laptops or smartphones. Now, we collected traffic in two bands for around 30 to 35 minutes. And we were mainly interested to capture traffic which are associated with AP discovery process. So in this case, the probe request and probe response. In the second experiment, we wanted to analyze what is the impact of discovery on Wi-Fi latency. Now, what is Wi-Fi latency? It is the latency between the client and the last hop connected access point. So in our experiment, we had a Wi-Fi which was connected to Wi-Fi hotspot server, and to measure time, we relied on the ping utility. So in this case, we measure round trip time, which symbolizes very similar to Wi-Fi latency. Now, while doing this experiment, we made sure that the client is actively trying to search all the available access points. So it was triggering an AP discovery process after every 2 minutes. We also made sure that all the background traffic is disabled to get the realistic measurements. Now, let's try to understand what is the impact of active discovery in terms of spectrum wastage. Now, probably this looks very complex diagram, but let me simplify it. for you. So we have a Wi-Fi client, which is trying to discover access point. There are multiple access points in the network. Now, let's imagine that these are the group of APs which are operating on channel number X. Now, this client, to search for an access point, what it does, it sends a packet, a special management packet called probe request. After sending probe request, it waits for a time. This time is called minimum channel time. This is usually a time to simply sense a channel. If it finds any kind of activity on that channel, it will wait for a time called maximum channel time. So during this time, there could be multiple APs who responds to this probe request with probe responses. Now, after max channel time, basically client switches to discover APs on the next channel. Let's say in this case, X plus one. So now this process is called active discovery. And probably you may also recollect that there is other type of discovery called passive discovery, which simply relies on the beacon packets. But usually the client follows more active discovery than the passive discovery. So the problems which are associated with active discovery are more important to investigate. So here we focus mainly on active discovery. So as I said earlier, so this is the active discovery. And as you can see, there could be multiple retry frames. Now, what is retry frames? So whenever access points send the probe response, it expects that the client will respond back with the acknowledgement. So if the AP did not get any acknowledgement, it will try to simply resend these probe responses. And these are the retry frames. In our captured traffic, what we found that around 75% probe responses were retry frames. So now imagine that these retry frames are trying to congest the network. The other issue that we found that some of the probe responses were sent after the max channel of the time. So the client, which was earlier operating on channel number X, is already moved on to channel number X plus one. And the APs are still trying to send the probe responses. Now, both the retry frames and the frames which are sent after max channel time are simply redundant for the client because they are not useful for this client to discover APs. And in our particular case, we found around 62% probe responses reach after max channel time. Now, the question is, how to minimize this number of redundant probe responses. Now, why this is important? Because these probe responses are sent at the lowest order of modulation scheme, probably BPSK or QPSK. So they consume a lot of spectrum airtime, and this results in the spectrum wastage. And this is not something new. A lot of people in the literature have stated this issue. So these are the references you can find. Now, the next problem that we found was with respect to Wi-Fi latency. So as we collected Wi-Fi latency with the ping utility, what we found that whenever client triggers active discovery, the latency shoots up from, let's say, 5 millisecond to up to 150 millisecond, and we have seen that it also lasts for few seconds later. So on the right hand side, we try to learn its distribution. So we plotted CDF, and in this case, we plot two things. One is when the client actively scans the network is called periodic active discovery, and when there is no active discovery trigger. Now, in this case, we can see that the median value of this latency is very similar. It's around 5 to 7 milliseconds. But what we observe that there is a long tail distribution. What does it mean? That 90 to 97 percentile value is very high as 150 millisecond delay. Now, why this is important? It has been studied in the literature that this kind of distribution where we observe long tail Wi-Fi latency, it could be around even 25 milliseconds. That causes an application level of delays, and these delays can result into a page load, and it could be as high as 2 to 3 seconds. Again, this kind of page load delay is very bad for the customer. If we observe that there are websites which are very slow to load, we will simply don't use those websites. Also, for the companies like Amazon, Facebook, they actually there is a monetary loss for those companies. So this is an important issue for them as well. So these are the two problems which were associated, and we try to analyze, especially related to active discovery. Now, again, question is how we are going to minimize this latency which is caused by active discovery. And to overcome these problems, we try to design the new approach, which is called CSIscan. And this is our vision. So this is very similar diagram as we've seen earlier. But now what happened? The client, instead of searching access point across all the channel, what it does, it expects some kind of information from the access point. Now, what does it access point does? This access point, whenever they are communicating with other client, they also encode some kind of discovery information. Now, this discovery information is leveraged by this Wi-Fi client, which wish to discover APs. And across all the channel, it simply processes physical layer frame, and within that also only CSI to extract discovery information. Now, just to emphasize, the client always processes all the physical layer frames, uh, and at the MAC layer, it decides whether to discard those physical layer frame or use that for the further processing. So this is not something we emphasize the client to do. The client already is doing that. Now, after processing all the channel and extracting discovery information across all the channel, it tried to find one particular better channel, let's say best channel or the better channel among all these channel, and only on that channel, it simply follows the regular AP discovery process. So this is very simple. Now you may ask, how does AP encode the information? How the client discovers, decode this discovery information? And that is what CSI scan contribution is. So just to recap, what is CSI? This is what our major focus is. So before we jump into, let's try to understand what is CSI. So as we know, CSI is represented into two things. One is magnitude and the phase plot. Across x-axis, we have the subcarrier index. In this case, there are 52 subcarriers. Usually if we have a 50 size of 64, we use only 52 subcarriers. In our case, we don't usually rely on the magnitude plot, so we will only concern about the CSI phase plot. We also do two kinds of post-processing. The first post-processing is called unwrapping. So as we know that the phase is usually wrapped between -180° to 180°. And here we have a discontinuity. Now to remove this discontinuity, we do some kind of manipulation of adding 2π and -2π. And by doing that, we get very linear straight line. So this is the first post-processing that we do. After that, subsequently, we do another post-processing, which is called detrending. So it's simple that we just basically remove the slope of this line and bring it to 0°. So here we have a very approximately linear line around 0°. So these are the two post-processing steps that we do. Now how does AP uses LTF and the client uses LTF to estimate the CSI? So on the left hand side, we have a sequence of X of K, which is in the frequency domain. This is the sequence which access point uses. This is a fixed sequence. This is the frequency which is used, and this is in the frequency domain. So after OFDM, after IFFT, we get a time domain sequence, and this time domain sequence is called legacy long training field. So this is the field which is a part of the Wi-Fi preamble, and this Wi-Fi preamble is used by the client for the channel estimation. So as we have seen on the right hand side, the client has plotted, we have this CSI. So on the right hand side, we have a CSI phase information, and on the bottom, we have process CSI phase, and these processes includes unwrapping and detrending operation. So now let's imagine that we have the same sequence X of K on the left hand side. Now let's say there is one field which is one value, and we add a deliberate phase distortion of 40°. So instead of using value 1, let's say we use a complex number. So now what is the effect on the CSI? So we see there is a jump in the phase shift. So the effect of distortion at the AP side is visible in the CSI at the client side. And this effect is also channel independent. For the different channel distribution, we still see the similar phenomena in the process CSI phase. Now this effect is, so there are two information which are important here. Now, what is the subcarrier index which is used, where exactly the modification has been done. So here, as we did modification in the subcarrier index -16, so we see similar effect at subcarrier index 16, and how much phase distortion was added. So here we can see around 35 to 40 degree of phase shift. And the question is, can we introduce phase distortion in more than one subcarrier? The answer is yes. We can also introduce phase distortions in more than one subcarrier. So what we are doing here, we are intentionally modifying the LLTF at the access point, and those effects are visible at the client side in the process CSI. Now, how do we use this? How do we leverage this to encode some kind of meaningful information? So now let's say we have this sequence X of K, we divide it into several groups, and let's say we focused on only on one group. Now, in that particular group, we have, let's say we have two mapping tables. In the first mapping table, there are different phase distortion, different level of phase distortion. On the right hand side, we have the index mapping table, which decide which subcarrier index was modified. So let's say we are trying to modify, or we are trying to add a phase distortion in the 0th subcarrier index, and we have a choice of introducing different level of phase distortion. So in a way, that we can also add the similar phase distortion at different subcarrier index. So now the total number of bits that can be stuffed only in this particular group is defined, is can be evaluated by this formula. So now just to take an example, if L is 1, let's L is the number of indexes where we introduce the phase distortion, and we have a choice of 4 levels of phase distortion. In this particular example, we can carry 3 plus 2 bits of information. So overall 5 bits per group, and we have total 6 group. We can carry 30 bits of information per Wi-Fi packet. So this is the way of encoding information by deliberately or intentionally adding the phase distortion in the LLTF field. From the decoding side, let's say this is an example of the encoding on the left hand side. For the decoding, we can simply, so this is the CSI, process CSI phase at the client side. We can simply divide into different thresholds and determine determine where exactly the phase distortion is added and how much distortion is added. And we can use, the client can use similar phase and the index mapping table to decode this information. So this is just an example of it. So here at subcarrier index 19, we introduce phase distortion of 20 degree, and we can see a similar phase distortion. At subcarrier index 19, we observe around 21 degree of phase distortion. So this is an example of CSIscan decoding. Now imagine that as we introduce the phase distortion in number of subcarriers, we try to evaluate what is the impact on the packet error rate. I think many people would have this question. So that's why we evaluated in a simulation what is the impact, and we observe that as we increase the number of subcarriers where we introduce phase distortion, the packet error rate increases. This is also true as we increase the level of phase distortion. This is also true as we increase the MCS value of the packet. So for example, if we use QPSK over 16 QAM, the packet error rate is going to increase. Now just to keep packet error rate within some threshold, we can opt for decide that the number of subcarriers is 1 and the level is 1. Like we can minimize the packet error rate, but this will allow us to transmit only 3 bits per packet. Now this is not optimum to transmit any kind of meaningful discovery information. So we need to to improve the data rate, to improve the number of bits that we can stub, we'll have to find some upper bound on n and theta. Here n is the number of subcarriers and theta is the maximum phase distortion that we can add. So we have to select this value dynamically so that the packet error rate will always be within some threshold. Now to do that, we try to use machine learning. So how does this machine learning operation work? So let's say we have access point, and there are 2 types of the client: associated client and the discovery client. So as just to recollect that we are leveraging the communication with associated client to send an information for this discovery client. So for that, we rely on the previous transmission from this associated client, and we estimate the CSI and the SNR. So this will give us what is the channel quality for that particular link. Also, for the next outgoing packet, which is intended for this associated client, what is the MCS value which is used? And then we use a machine learning approach to decide to determine what is the optimum level of n and theta. And we, in this case, we try to use CNN. And these were the 4 classes that we use in our particular class. Of course, this we can have different choices, but these are the choices that we choose to select in the CSIscan. So basically, CSIscan classifier will decide one of these classes, and once we know what is the level of n and theta, we can use CSIscan encoding block to modify intentionally the LLTF field, and that will be our next outgoing packet, which is intended for associated client, but also leveraged by discovery client to extract the discovery bits. So this is the overall operation of the CSIscan. So this is the convolution architecture that we use. I won't go through the detail. This is very simple architecture, and so our novelty is not designing in the architecture, but the way we have used and the way we have designed, the way we have designed the input and the output. Our main contribution was using supervised domain adaptation. Why? Because we decided that to capture traffic in a real environment is really painful. We also, once we capture traffic in one environment, it's not useful in other environment because the environment has changed. And for that, we try to use the simulation environment we have, where we have the with limited effort, we are able to capture a lot of traffic, and to train neural network, we required a lot of traffic. So we try to train the neural network with the data collected in a simulation environment, but to work this in a real environment, we had to use some kind of domain adaptation technique. In this case, we use supervised domain adaptation technique. In that particular, we use fine-tuning approach, where we froze the neural net only the convolution layer, where we observe that this convolution layer is able to learn the parameters, learn the specific features, and which is basically learned by the data collected in a simulation environment. And for real test bed, we use this fine-tuning approach for domain adaptation. Now let's go through the performance evaluation section. So this was our experimental setup. We had associated and the discovery client. So just to compare with the traditional active discovery, so active discovery protocol, actually it scans all the 39 available channels. So including 2.4 and the 5 gigahertz. On the other hand, our CSIscan only scans one channel. Now, in our case, we decided to channel one particular channel upon successful decoding of the information bit. If it is not able to decode this information, it scans all the 39 channels like active discovery. So this was our performance comparison protocol. What we did was, our discovery information is encoded in every traffic that was intended for the associated client. So this is kind of way of aggressive discovery protocol. So we wanted to analyze what is the worst case performance, and we tried to use this below metrics. One is how many number of probe responses generated per probe request, what is the latency. Also, we try to analyze what is the CNN accuracy, and how much bits we could actually stuff inside the packet on average, and what is the packet error rate. This was our deployment scenario. We considered three cases, where in first cases we had stationary and line of sight associated as well as discovery client. In second case, our clients were non-line of sight from the AP. And for the third case, we wanted to evaluate with the realistic scenario where both the clients were moving. So this is our evaluation. As we see that the left-hand side plot, we try to analyze the distribution of number of probe responses. What we observe that the number of probe responses which is generated per probe request on average has reduced from 22 to 6. So overall, it reduces the probe response by 72%. So this will help to save the spectrum over airtime, and in a way it will reduce the spectrum wastage. For the second case, we try to observe what is the long tail, whether we observe any kind of long tail distribution. And in that case, we observe that the 99th percentile value was reduced from 132 to 6 milliseconds. And for the CNN accuracy, with the simulation data, we got accuracy around 95%, where we use 80,000 example. On the other hand, for a live environment, we were able to get very similar accuracy of 93%. The real benefit was we only used 12,000 training examples. Now this is an bit stuffing efficiency plot. On the left hand side, we try to compare how many discovery bits were stuffed per packet on average, and on the x-axis we have different MCS rate modulation schemes. We compared with different approaches. The first approach is overly pessimistic approach, that using always the low value of n and theta. Other is overly optimistic approach, always go with the high value of n and theta. Moderate is like the moderate value, and the CSIscan basically dynamically select the optimum value of n and theta. Now, what we observe that I think I'm.
Well, yeah, ask you to wrap up.
Yeah. So let me summarize this slide. So basically, we try to compare the bit stuffing efficiency with the CSIscan with other three approaches, and we observe that CSIscan is able to stuff very high bit stuffing efficiency, very close to optimistic approach, but is still able to maintain very low value of packet error rate. Just to summarize, this is novel AP discovery method, and our contribution was how we encode discovery information and how do we decode it. Also, we designed CSI to learn the optimal level of n and theta. Also, of course, we developed the proof of concept as well with the USRP, AP, and the client. And these are some results that we found. Thank you. So you can ask questions if you have.
Thank you. Thank you very much for your talk. I think it was very clear, and for your contribution. So actually, so I do have questions, but I want to ask if anybody wants to start before ahead of me. So does anybody have questions that they would like to ask Kunal? So if not, I will go first. And the thing that crossed my mind when I read your paper was, okay, you could use this for AP discovery, but you could use this, I mean, it's just like a side channel, right? You could use this for pretty much sending any kind of information or disseminating any kind of information, right?
Right. So I think you get the right point. Yes. So our main contribution was, of course, it's a side channel, and we can use this information for any kind of application. In fact, actually, our second extension was, which is still yet to be published, we use it for different application. But of course, we choose discovery as a main application where we find it very interesting, especially for a dense Wi-Fi network where we are going to have 82.11x protocol. What we observe that there is one particular preamble which is legacy LLTF field, which is very common for any kind of protocol, and it is mainly used for to provide backward compatibility, and we wanted to leverage this for solving mainly critical problems. So we chose this application.
Yeah. So yeah, I think also for service announcements for many things actually. So
correct. That's correct. Yes.
So another question. Well, this was a broad, and I know it's a very detailed, but which information do you actually send in the side channel? What do you send? Because I mean, you describe how you modulate and how you demodulate that information, how many bits you put, and how. But okay, what is the meaning? What do you actually send for your application?
Right. So in our case, we chose very simple example, simple information, which is, so usually AP always carry information like what is the spectrum load on that, what is the AP load, how many users are connected to this access point. So these are the examples. These are the information which is usually in the either probe request packet or or probe response packet. Of course, we have in our case, we are able to embed around up to 60 bits. So we may not able to encode the entire information as MAC packet, but I think we chose only two information which can easily encode it with 60 bits.
Okay, and which were they? So which are the most important information to choose the EP of all the information that is sent?
So I mean, for
different combinations, or did you just take two and go with those two?
Right. So we thought let the network administrator decide what information it wants to encode. So we didn't decide on that. We thought of using as a simple information. So this is up to the network administrator.
Yeah. Okay. Yeah, that was quite it. So does anybody else have questions? I mean, I can. Anything you would like to ask? I don't see here. Sorry, you have. I don't see any. Okay, there's a message here of somebody who wants to. So it's just for me. So no, it's not a question for you. Okay, so I would like to ask one final question, which is about your generalization. I thought it was quite interesting to do the simulation, train the network on simulated data, and then just do what you call this parameter fine-tuning on real data. My question is how close was your simulation from the actual environment? And
right.
If your actual environment would be very different, would it still perform so well with, okay, like 12K data points is very, very little?
Right. So in our case, we use MATLAB channel model, which was WLAN AC channel model. So it uses very close, it uses the realistic measurements to generate a channel model. Of course, the realistic channel would be slightly different. And what we observed that when we simply use the model which was trained with the simulation data and directly apply on the real data, it performed very poorly. And that's where we had to use some other approach, and we find this domain adaptation technique to be useful, where we had to collect data in a real environment to again probably to work very similar to the simulation environment. So in our case, yes, of course, we had to retrain it with the new data that has been collected, but we observed that like the features, the channel models are very similar, like because the MATLAB uses the WLAN AGC channel model with the real measurements that has been collected.
Okay, thank you. So if nobody has any more questions, come on, this isn't it. Then let's go to the second talk, which is 6 feet apart, a protocol for physical distancing on a customizable wearable. So thank you, Kunal. Yes, you can change. And now I think it's Yifeng. Could you turn your camera on? Yifeng is a second year PhD student at Georgia Tech, right?
Yeah.
So I am not seeing you. Can you turn on?
Sure.
Camera? Okay, yeah, great. So this is Yifeng Kao. Now maybe you can turn on your presentation.
Okay. Okay, thanks, Anna. And I will share my screen. Yeah. Can you see my screen now?
Yes, I am.
Okay, so I will start. Hello, everyone. Welcome to this talk of 6 feet apart, a protocol for physical distancing on a customer wearable device. I'm Yifeng Cao from Georgia Tech. The recent COVID-19 has increased people's awareness of the importance of the public health. One of the easiest and the most effective way to prevent the virus spread is to keep 6 feet apart from others. However, in crowded areas such as hospitals or supermarkets, people may find it very hard to know exactly whether they have at least 6 feet from others. So we want to build such a system which can warn the user when he enters 6 feet of others. This device will trigger a audio and the visual alarm when he is too close to others. We want to ask this question: can we embed this physical distancing function into a wearable device? This system should meet at least two goals. Firstly, this system should be low cost. To be low cost, it should be both infrastructure-free and reconfiguration-free. Being infrastructure-free, meaning that we don't want to deploy any central servers in the real world. Being reconfiguration-free, meaning that we want to minimize the maintenance fee as much as possible. The second goal is to be lightweight. Being lightweight makes this system easily hidden in daily items such as shopping carts, the identity card, and the smart wristband. Building such a system is non-trivial. There are at least 4 challenges. The first challenge is the limited resources of the embedded devices. We must make sure that our algorithm can run smoothly even in devices with only tens of KBs of memory with very limited power. The second challenge is the peer-to-peer ranging with dynamic participation. We want to make sure that every node is able to enter and leave the network arbitrarily without interrupting the running of the algorithm. Thirdly, to achieve real-time ranging is very hard. In a distributed system, we know that do the pairwise ranging is inherently an O(n)² problem. So we have to deal with each step in this process very carefully to reduce the time as much as possible. Finally, to deal with the complex wireless environment is very hard because of the uncertainty of wireless communication. To overcome the above challenges, we designed 6 feature part. 6 feature part is designed for physical real-time physical distancing on wearable devices. The prototype of 6 feature part is shown in the right-hand side. There are 3 key functions for 6 feature part. They are an ultra-wideband radio-based ranging algorithm, a P2P ranging protocol, and an occlusion detection module. Here is an overview of 6 feature part. In the lowest level, the UWB module will decide what method we would use to get the distance measurement and what type of information it needs to provide to the upper level for future analysis. Basically, we would provide the channel impulse response and packet timings. Then, the P2P ranging protocol will accept the packet timings as the input. It provides a robust protocol with which every node in the network can exchange packet timings with other nodes, which is required for distance measurement. Additionally, there are 3 submodules in the P2P ranging protocol: a time slotting scheme, a slot adaptation algorithm, and a response again scheme. They are designed to reduce the time cost. They can substantially decrease the multiplicative factor of the time complexity, making 6 feature part feasible in the real world. Finally, we have an occlusion detection module, which accepts channel impulse response and road distance measurements as the input. It uses these inputs to extract a couple of features and send them into a classifier to classify 3 different kinds of occlusion. They are line of sight signal, wall occlusion signal, and human occlusion signal. Then the occlusion detection module will deal with each type of occlusion correspondingly. Let me talk about the UWB module at first. We choose ultra-wideband as our base signal for ranging because it has several good properties. Firstly, it can quickly achieve accurate distance measurements with tens of centimeters error. By averaging multiple packets, this error can be reduced to about 10 centimeters, which is enough in our M scenario. Secondly, UWB has 1 GHz bandwidth. Such a large bandwidth makes it very defensive to the multipass problem. And finally, UWB can provide nanosecond time resolution, with which we can directly compute the distance measurement from the time of flight. So basically, we can directly compute the distance by multiplying the time of flight with the speed of the light. However, since the transmitter and the receiver don't share a common clock, they are not synchronized very well and have a clock offset of about tens of milliseconds. And this clock offset will incur huge errors. So we adopt two-way ranging to solve this problem. Two-way ranging is taken from IEEE standard and is a widely used protocol for time of flight-based indoor localization. Suppose there are two nodes in the network, node A and node B. Node A will firstly initialize a poor message. After node B receives this poor message, it will reply with a response message. After node A receives this response message, it will return with the final message. And with this final message, node B can compute its distance from node A. During this whole process, we will get six timestamps, T1 to TA3 and TB1 to TB3. With these 6 timestamps, we will get 4 time durations, RARB and DADB. So we can get the distance from the formula in the slide. This formula is a little bit non-intuitive, but we can find the derivation in the reference at the bottom of this slide. However, simply adopting the two-way ranging doesn't solve everything. What makes for one device pair doesn't scale to multiple users. There are 2 problems left. The first problem is the coordination of medium access. In a distributed system, every node has no knowledge of the existence of other nodes at the very beginning. So if we don't have a good coordination policy, the whole transmission will be in a mess, because every node will try to send the packets arbitrarily according to its own timetable. The second problem is the time consumption. Remember that for every in the two-way ranging, for every distance measurement, we will need 3 packet transmissions. So if we perform P2P ranging, the packet transmission will be really huge, and it will result in seconds of lag in the real world, and it is unacceptable. So we propose a P2P ranging protocol to solve these 2 problems. Firstly, to reduce the time cost, we will use the broadcasting nature of the wireless signal. Instead of sending the poor and the final message independently to every receiver, the transmitter will broadcast the poor and final message. This broadcasting will reduce the packet transmissions to about 1/3 of the original. However, the broadcasting brings in a new problem. When the receivers receive the poor, because of the property of the broadcasting, they will receive the poor almost simultaneously. So if they still choose to send the response immediately, they will have a great chance to collide with each other. To solve the collision problem, we propose a time slotting scheme. At the very beginning, we will allocate a couple of available time slots to the transmitter. The number of time slots will be attached in the poor message. When the receivers receive this poor message, they can randomly choose one time slot within which they can send the response. So in this scheme, if every receiver chooses a different time slot, they won't collide with each other. However, this scheme doesn't solve the problem completely. There will always be cases when different nodes accidentally select the same time slot. So we propose 2 solutions to solve this problem. The first solution is a slot adaptation algorithm, which can dynamically select the optimal time slots at the transmitter. The second solution is a 2-round P2P ranging scheme, with which every node who fails to send a response or experience a collision will get another chance to send a message called response again to complete their distance measurement. For the first solution, The purpose is to maximize the efficiency. And we observe that the collision rate is tightly coupled with the number of the nodes in the network and the number of the slots. So if we have an expected collision rate, and if we can somehow estimate the number of nodes in the network, we can get hints on how to select the optimal number of slots. And fortunately, the network size can be estimated from the occupation rate in the first round. So here, the occupation rate is the occupation rate of the received responses. So we can directly select the optimal slots with these two parameters. The second solution is a response gain scheme. In the first round, we noticed that some of the receivers will send the response successfully, like user 4 in this slide. But others might experience a collision. But whatever, the transmitter will collect all the received responses in the first round and put them into a receiving list. This receiving list will be attached in the final message. When other receivers receive this final message, they will check if they have already been in this receiving list. If they are, like user 4, they will not respond to this final message, and we will let it go to sleep for a while to save some power. For other users, like user 2 and user 3, they will find they are not in this list. So they will send the response again message to the transmitter. After some time, the transmitter will send a final again message for these users to complete their ranging process. Let me briefly summarize what we have done for now. What we already have is a robust low-level algorithm to get the distance measurement and a protocol to perform the P2P ranging efficiently. But at this time, we want to ask this question: should all the distance measurements be treated equally? Actually, it's not true. And that's why we have an occlusion detection module. Remember that we want to classify 3 different types of occlusion: the line of sight, the wall blocking, and the human blocking. For the wall blocking case, it's very natural to think that even if the user came into the 6 feet from another user, the system shouldn't warn the user because there is no risk of infection. We observe in the channel impulse response that the channel impulse response of wall blocking has a much lower amplitude compared to the line of sight signal. So we can use this feature to classify the wall blocking case. For the human blocking case, we think we still need to warn the user when he is too close to others. However, we find that the distance measurements are erroneous in this case. So before the system gives a warning, the distance should be compensated. Similarly, we observe in the channel impulse response that the CIR of human blocking not only has a lower amplitude, but is also interfered with a closely coupled multipass. And we will use this feature to classify the human blocking case. Based on the above two observations, we will firstly extract the channel impulse response in the lowest level, and then use the channel impulse response to extract a couple of features. With these features, we can build a decision tree, which is used to classify the occlusion, and build a regression tree, which is used to compensate for the distance measurement. All of these functions are integrated into this embedded device, which has no cloud and no internet connection. Finally, let's go to the evaluation part. We evaluate 6 feature part on the Decawave Track 1000 toolkit and Adafruit Feather M0 with DW1000 chip. We use the modified IEEE standard two-way ranging modified two-way ranging in the IEEE standard as the baseline, and we call it arbitrary two-way ranging. We focus on three metrics: the percentage of the rangings completed, average ranging time, and the classification accuracy. Firstly, let's look at the percentage of rangings completed. In a 10-node network, we can see that 6 feature path can reach over 60% packet reception ratio. And in the same case, it's very hard for arbitrary two-way ranging to do any valid distance experiments. For the average ranging time, it determines how long the user have to wait to get the distance measurement. We find that in a 10-node network, 6 feature path can perform the pairwise two-way ranging in 1 second, meaning that every node in this network can get the distance from every other node in 1 second. It corresponds to approximately 10 Hz ranging rate. And when we see the arbitrary two-way ranging, the performance is much worse. Finally, let's look at the classification accuracy. We test our classification accuracy in 3 different scenarios corresponding to low multipass, medium multipass, and high multipass. We achieve an overall accuracy of 85%, but we also observe that as the multipass level goes up, the accuracy decreases a bit, and most misclassification happen between the wall occlusion and human occlusion. There is some future work remained for 6 feature path, and actually this work is already ongoing. Here is a prototype we will use in the real world. We want to deploy our 6 feature path in the real world to collect the data on a large scale for future analysis. We also want to do some more exploration with some new sensors like AMU to understand people's behavior. To conclude, in this work, we designed a robust P2P ranging protocol which can perform the pairwise distance measurement. Secondly, we classify 3 different types of occlusion, enhancing the feasibility and generality of our 6 feature path. Finally, we develop a working prototype with low power, lightweight, and small size. And for more details, we refer you to this website for the code and the paper.
Thank you.
And thank you. Yeah.
Yifeng, thank you. We are already over time, but I think it's okay. You were finished.
Sorry.
So thank you very much. Very, very interesting work. Very timely, right? I think so. Providing at least some solutions to some of the main criticisms on the use of Bluetooth for estimating proximity. So anybody has questions? Show me. I see you turning on your camera.
Yeah, I was waiting for this before I sleep. Okay. Yeah, the talk is very interesting. The question is, you're getting so much complication that it's, the wearable device is very much abundant if you have a smartphone, typically. So in Germany, we use this kind of, COVID-19 tracing app. Actually, it's a Bluetooth enabled, but it's primarily based on the signal. So the question here is developing this distance measurement specific hardware, is that too costly, or whether it can be put in an existing device like smartphone or iWatch or something as an app? Let's say not as a dedicated hardware to do all this protocol design, but whether you can move up to the application layer, so that you just utilize some low-level service rather than developing long protocols and hardware and also co-design, right? So software, hardware co-design. This is very complicated and costly.
Yeah, thanks for this question. I like this question because it is a very practical problem. Actually, firstly, there is an opportunity to move our design to the application layer, although we cannot do it right now. recently there is some news that the Apple, the iPhone, and the Samsung will embed the UWB chip in their smartphones. So we will get this opportunity to move the whole design up to the applicational layer. And for the cost problem, I will take our current setup as an example. The cost of this whole setup is about $30. So I can so it's not a very high
it's
cost.
about
I
the
think.
equipment cost, but you didn't consider the development and the deployment,
That's true.
right?
Yes. But it is a distributed. It is a distributed system. We build it in a distributed manner. So, so if we want to deploy this kind of equipment, we just put this on something like shopping carts, and we don't need to do anything else because we don't need to connect it to the internet, and we also don't need any central servers. So most of the cost will be the label cost and the equipment cost.
I would like to add one point here, if I'm allowed. Do you think? I think like even Apple and Google tried to use it. I think before the coronavirus pandemic, like very initial early stage, right? But they were the issue was with the privacy, that they collect a lot of private data. So I think your approach is like you're not collecting any private data, so that could be one benefit, I would say. Is that correct?
Yeah, that's true. Yeah, that's true.
So you don't store, let's say, which device ID you have met. You eventually you need to record this basic information, right? So the device ID is unique, so that you can
This is a
follow up, right?
Yeah, the device ID is unique, but it's only used in the experiments. If we want to put it in the real use, there is no need to collect this information.
Because I think this is a real-time detection, right? That you are looking at.
Yes,
Okay.
there is and there is no connection between the device ID and the user.
This is a real time. It's just like for
okay. If you don't want to check whether you encounter a same person or same device, then there's no need to record it in the future. But
yes,
if you want to do detailed analysis, you probably you need to record the device ID you encountered.
Yeah, that's true. But that's only for experiments.
Yeah. Okay.
I would have one question. You mentioned, for example, embedding it in a shopping cart. That sort of by itself changed completely the power delay profile. Would your classifier still work in that case?
Sorry?
So if you embed this UWB hardware or not, its communication is usually very sensitive to any kind of propagation effects because of the wideband, right? So it's very selective in frequency. In time. So once you put it on a shopping cart, aren't you going to have, you use these timing delays to the power delay profile, you use it to detect the occlusions. But if you put it on a shopping cart, you are going to have a different power delay profile alone from the shopping cart, I guess.
So yeah.
The question is, would your classifier be robust to that?
That's true that the shopping cart will have some effect on the power profile, and it's actually a generality problem. If the occlusion, actually we have some for this specific problem, the occlusion of the shopping cart is not very big, but if we consider generalize it to a bigger problem, which is where the shape or the thickness of the occlusion will have some effect. Actually, it has some effect. So we have to. So in our setup, we basically will consider all the occlusion will have a a similar thickness. So they will have, so the power profile will not have a significant difference with each other.
Okay. So does anybody else have questions? Because otherwise we would move on to the next talk.
So I had one question. It was around so it was around the collision problem that you were having, and I was just wondering. And I mean, I'm going to be talking about this in my talk in a minute or so. But if you've considered using concurrent transmissions to avoid that collision problem, I know there's a number of papers that look at sort of UWB localization and employ concurrent transmissions to that effect. So I just thought it might be a good way to kind of handle that issue.
You mean concurrent, using the concurrent transmission to? Okay. Yeah, I think it's a very potential technique, but basically using concurrent transmission, we think that it might need some revision in the physical layer, and actually our protocol is a MAC layer prototype. The benefit is that we don't need any revision of the physical layer, and we can use the commercial devices to do it directly. But yeah, but I also think the benefit of concurrent transmission is that it can somehow get more real timeness than the MAC layer. I think it can be a trade-off in the real world.
Yeah, sure. But I mean, the answer you gave there, you know, the fact that you don't need to actually modify the physical layer, I think is a really important point.
Yeah. Okay, thank you very much, Yifeng.
Thanks, Anna.
Welcome, Michael.
Thank you very much.
Michael is a senior research engineer at Toshiba, Bristol, and he just received his PhD from the University of Bristol, as I see, and he's working on adaptive networking, control solutions for IoT. And he's presenting an article on, a paper about the impact of physical layer on the performance of concurrent transmissions, which is, I guess, why this, but it's actually a very interesting idea to combine concurrent transmissions with UWB to address this problem. So go ahead, Ben.
Cool. Can you see my screen, just to double check?
Yes, I can.
Fantastic. Okay. Yes. So as we just found out, you know, I'm working on concurrent transmissions, and this is kind of the topic of this paper. So specifically here, we're looking at the impact of the physical layer and the choice of physical layer on the performance of concurrent transmissions. And this is actually a collaborative effort, not only with Toshiba here in Bristol, but also with TU Graz in Austria, with RedNodeLabs in Germany, Nanjing Agricultural University in China, and also SARI in China. So I'm firstly going to look at what are concurrent transmissions and what are the physical layer properties that enable them. I'm then going to look over some recent work that explores or highlighted the fact that concurrent transmissions can actually work over multiple physical layers, specifically the Bluetooth 5 physical layers. Then going to look at the first set of experiments that we did on one-hop CT performance, with focus on the beating effect and how this actually affects the performance of your receptions. And then also look at some network-wide experiments that we did, examining multiple different concurrent transmission primitives over various jamming scenarios and over various packet lengths as well. And then finally wrap this all up with some recommendations for the design of multi-PHY concurrent transmission protocols, which are enabled by modern wireless power low-power wireless chipsets that can actually support multiple physical layers on the single radio. So firstly, what are concurrent transmissions? So we all know that when two nodes transmit at the same time, they're going to collide at the receiver. And this is something that's pretty fundamental. You learn this at university. But concurrent transmissions is the technique of actually intentionally allowing highly synchronized devices to transmit at precisely the same time. The original glossy paper back in 2011 found that if nodes are sufficiently well synchronized to within half a chip period, which is 0.5 microseconds for 15.4 and something like 250 nanoseconds for the 2 meg Bluetooth 5 physical layer, then you can actually reliably demodulate the transmission. And this applies for nodes that send the same data. So you're sending the same packet data. And what happens is that your reception benefits from non-destructive interference. This was previously attributed to constructive interference, and I'll go into some detail later as to why it's not constructive interference, but essentially allows you to reliably receive that transmission. Later on, it was also found that these transmissions were benefiting from the capture effect, as they're frequency modulated transmissions, and this is where if you have multiple signals being transmitted, you can actually reliably receive one of the transmissions as long as it's received with sufficient power over the other signals. And this is about 3 dB and 15.4. And this is very useful for sending nodes that are sending different data, so you can still receive that data. So given that we've got these two physical layer properties, we can then begin to build up synchronous flooding protocols based on these concurrent transmissions. And synchronous flooding allows the network to reliably send a packet across the entire mesh and broadcast this to the entire mesh. What happens is you have an initiating node will transmit, all of the nodes will receive, and once they receive, they begin to transmit synchronously with that initiating node on a time-triggered basis. And this gives us extremely high reliability, even under external network interference such as Wi-Fi, but it also allows us to transmit a packet with minimal bounds and latency, depending on your physical layer. So it eliminates delays caused by scheduling or backoff mechanisms. So I mentioned that we have non-destructive interference, and we also have the capture effect. But there's also something called the beating effect, which the community's kind of recently realized comes into play here. So the beating effect happens when you've got errors in the manufacturing process, which cause subtle variations in the carrier frequency offset of the radio oscillators. And this actually results in a sinusoidal envelope of both constructive and destructive interference across the packet. And we can actually categorize this envelope in terms of its periodic negative effect on the underlying transmissions. So you can have wide and strong, wide and weak, narrow and strong, or narrow and weak. And depending on the type of beating that's experienced, this can actually have a significant impact on the performance of receptions. So I mentioned that recently it's been shown that concurrent transmission-based protocols also work over the Bluetooth 5 physical layers, as well as the 15.4 physical layer. So this is the uncoded PHYs of 1 meg and 2 meg, and also the BLE5 coded PHYs of 500K and 125K long range. And modern chipsets such as the NRF52840 by Nordic is actually capable of switching between these physical layers with no additional radio overhead except for the radio ramp-up time. So I mentioned that the choice of physical layer, because of these different effects of wide and strong, narrow and weak, the choice of physical layer actually has a huge impact on CT performance. So in these diagrams here, to the left of these figures, you see that we reduce power delta. To the right, we increase power delta. At the top, we reduce the relative frequency offset between devices, and at the bottom, we increase this. And this actually gives us some very surprising results. For example, under narrow and strong beating, as we categorized earlier, when there's low noise, i.e. an SNR of over 20 decibels, the coded BLE 500K physical layer, which you would think should perform quite well, is actually surprisingly the worst performing PHY. So to date, there's actually been no extensive experimental study looking at how CT protocols perform across these different physical layers. It's relatively new. So we wanted to ask a couple of questions. First of all, how does beating, which is closely linked to the physical layer, impact CT protocols? At a network-wide level, how do constructed transmission protocols perform across these different physical layers? And then finally, are there any properties or observations that we can take advantage of in order to build up multi-PHY protocols? So in order to do this, we used a testbed. We specifically used the DQ testbed at TU Graz. And why do we need this? Well, using this, we're able to do thousands of jobs with over many thousands of hours and build up many hundreds of gigabytes of raw logs. It also gives us benchmarkable experimental setups with hundreds of different layouts and thousands of different node combinations. And importantly, you can actually batch schedule these jobs, so you can run many jobs overnight and then not have to worry about it. But also, with the current climate as it is, this was actually really good because, as I mentioned in the first slide, this is a collaboration with partners in Austria, with TU Graz, China, and also Germany, and here in the UK. So with the whole COVID situation, it was really great to be able to collaborate in such a way on the same testbed remotely. And the DQ has actually been recently updated with the board I mentioned earlier, which is the NRF 52840, that has all the Bluetooth physical layers plus also 15.4. So let's look at the first set of results, which is looking at the impact of the beating effect when you've got one-hop concurrent transmissions. So in this scenario, we're looking at all nodes line of sight in a single room. And what happens is that in this, for example here, you have source 2 will synchronize 2 forwarders. And then on the second transmission slot, all 3 nodes will actually transmit to the destination. So here you're actually able to control which nodes are transmitting and how many are, what sort of concurrent transmission is received at the destination. So we firstly looked at different CT pairs. This is 2 nodes transmitting towards the destination. And what we see, in some cases, there's actually no beating frequency seen whatsoever. But then, oh, sorry, I should have gone back. Yeah, so these results here actually show the bit errors across a packet that's sent, identical packet that's sent from two nodes. And what we did was we looked at the CRC of the received packet, and we then indexed the incorrect bits on that received CRC. So from this, over many hundreds, many thousands of transmissions, we're actually able to build up a histogram of all the errors. So what we found was that you can actually see this sinusoidal beating frequency just by looking at those bit errors. And from examination of different pairs, we could see that in some cases there's no beating frequency, but in other cases we start to see the narrow beating, the wide beating, the strong beating, the weak beating. So different device pairs experience different beating frequencies, and this is because they have these different relative carrier frequency offsets. And what we also noticed was that in the strong and narrow case, this beating effect can have a significant impact on the reliability of concurrent transmissions. In this example here, pair 8 experiences strong and narrow beating, and it practically decimates the reliability. We then also looked at what happens with the same nodes, the same pair of nodes, but you then do these transmissions over different physical layers. And what we see is that the beating frequency remains consistent as you go through all the file layers on that same node pair. In this example, is about 2 kilohertz. We also see that the BLE Bluetooth 125K coding is extremely robust against the strong and wide beating. But that surprisingly, the other coded PHYs, the 500K and also 15.4, don't perform well. But this is actually consistent with the modeling of the strong narrow beating conditions under low noise that we did in the paper. Sorry, hang on. There we go. We also looked at the density of concurrent transmissions, and we see that as you go from a single pair of concurrent transmitters up to 3 or 4, that the reliability drops fairly rapidly. But when you use the 125K coded layer, it can actually survive extremely high density concurrent concurrent transmission scenarios. But of course, you then incur extremely long transmission times due to the physical layer. And on uncoded PHYs, the reliability actually increases at higher densities. And we speculate this likely due to the received signal becoming a big bold multipath as you add additional concurrent transmitters. Whereas on the coded PHYs at higher densities, they actually begin to experience packet losses. And again, we speculate, but we think this is because the preamble was never heard. So yeah, this is the results that we did for the network-wide experimentation. So we're looking at different concurrent transmission primitives, and we're looking at the performance over various jamming scenarios and also different packet lengths. So we use 3 different concurrent transmission primitives, the first being glossy, which is where, this is from the original 2011 paper, which is where you interleave transmissions and receptions between the initiating node and other nodes in the network. We also use the example used earlier, which is robust flooding, which is a time-triggered approach, which also channel hops on each time slot. And then we also used a single channel variant of robust flooding in order to see what happens if you don't have this channel hopping mechanism. And D-Cube's particularly good for this sort of analysis because it's quite an interesting network. It's got areas of high density nodes, plus also sparse areas in the network. So yeah, as I mentioned, we're using 3 different protocols, 3 different interference scenarios generated, benchmarkable interference generated by D-Cube, which is no interference, mild interference, narrowband, and also strong Wi-Fi interference. We did these over all the physical layer options, so all the 4 Bluetooth physical layers, plus also 15.4. And we looked at 3 different performance metrics: reliability, latency, and energy. And we did this all for short packet lengths of 8 bytes and long packet lengths of 64 bytes. So what we find is that concurrent transmission protocols over the uncoded PHYs actually struggle even without external network interference, which is quite interesting. You'd think that because of the lack of interference, they would actually perform quite well. We also find that BLE125K, the long-range coded PHY, performs surprisingly poorly under external interference, particularly with larger packet sizes. And we believe this is due to the way that D-Cube actually generates the interference, which is periodic. And so that because of the longer transmission times of the BLE125K, it means that you're more likely to be cut off by that interference kicking in. We also find that 500K and 15.4 perform well under external interference. Oops, sorry. And there we go. And also that the robust flooding concurrent transmission primitive, the time-triggered one with the channel hopping, performs far better than the other 2 approaches. So, from those 2 sets of experiments, we built up some recommendations for the design of multi-PHY concurrent transmission protocols, which is particularly relevant given the capabilities of these new modern low-power wireless chipsets. And we also provide a handy cheat sheet for the design of these. So the first observation we had is that the 15.4 and the 500K PHYs are effective against external RF interference, but will suffer under the strong narrow beating conditions, which can cause a significant drop in reliability. To counter this, we recommend that in the absence of external RF interference and in low network densities, you can actually use the high data rate PHYs, or Bluetooth higher data rate PHYs, to in effect widen the beating so you're suffering less from it, and also transmission repetitions to exploit the temporal redundancy given that you're using a high data rate PHY. The second observation we have is that the high data rate PHYs, the 2 meg and 1 meg that I just mentioned, do help escape strong narrow beating, but they then exhibit poor performance in the presence of external RF interference. So, in the presence of this interference, we recommend that you use the 125K coded PHY, which is extremely robust, but only for short packets. Again, being such a low data rate PHY, it takes a long time to transmit. But it does allow you to escape beating, as seen in the previous slides. But of course, this choice should be made bearing in mind your application's latency, energy, and RF range requirements. Then finally, although the BLE 125K is effective against beating, it does perform poorly when sending long packets under external RF interference. So, in the presence of strong external RF interference, we recommend using the tried and tested 15.4, which is commonly being used in most of the concurrent transmission literature for shorter packets, but also then the 500K for long packets, as it has a similar response, but it transmits twice as fast. And that is the end of my talk, short and sweet. If you have any questions, please email me at this address, or alternatively, you can email one of my co-authors, Carlo, at the email below.
So, thank you, Michael. Does anybody have questions? About this paper or about the talk?
No questions.
No, this is I think maybe this is a different, so you're on this reliability and sensor network field, which is, I think, maybe not so usual or not so common. And so in that sense, this is it's a bit different.
Absolutely, yeah.
I think it was very, I mean, I think it's interesting. I think it's, it does provide some guidelines, but one question is, you're saying that these small sensor networks, we're talking about, I mean, what you call long packets are like 64 bytes, right?
Yeah, so it's long packets for transmissions. Yeah.
And my question is, what kind of, so, under what basically says, under strong interference, you can send almost no data, right?
Well, no, I mean, you can. Again, it depends on the physical layer that you're using. But this is kind of where we're trying to pitch this towards the design of multi-PHY concurrent transmission protocols that can sense the network conditions and, in real time adapt to those conditions in order to give you the best performance under various interference. And I mean, the interference itself could be transient. I mean, there's no guarantee it's going to be there the entire time. So maybe you do want to switch to a different physical layer for a short time to boost performance, and then switch back to maybe using the high data rate physical layers. Just another point as well, in the one-hop beating scenario where we actually built up those histograms, that's actually using the maximum transmission unit, or close enough. I think it's about 200 bytes, something like that. So you can send longer packets using concurrent transmissions. And you can even send, if you use, for example, 6LoWPAN, which can fragment packets. I haven't done this yet, but it's foreseeable that you could fragment an IPv6 packet and transmit it using concurrent transmissions. It's entirely possible.
This is a design for reliability, right? This is not a design for throughput, and this is not for video. I mean, this is for reliability. If you're in an industrial environment sending command packets, and you really get them out, right? So
I get what you're saying, but so yes, I think the focus of this paper is definitely reliability and that performance, and not looking at throughput. However, on a side note, I would say that in terms of network throughput, this sort of technique can really help certain situations. For example, Toshiba, we do a lot of industrial IoT sort of scenarios. One of the things that we're particularly interested in is smart metering. Mm-hmm. And these can be, the smart metering we do tends to be sub-gigahertz, and this is really looking at 2.4 gigahertz, but the same thing still applies, is that if you got a tower block, for example, in Tokyo with maybe 1,000 different smart meters, and you want to update the firmware of those smart meters, how would you do it? Mm-hmm. So concurrent transmissions provide you with a very reliable mechanism to actually be able to send out a lot of data very quickly.
So that's actually a very interesting use case. But I mean, it's dissemination, right? You want everybody to get the same thing. It could be big, but you can leverage concurrent transmissions to. And actually, okay, exactly. This is dissemination protocols, right? All the protocols you use, they are dissemination protocols. So you want everybody to get the data.
Yeah, correct. Just to a bit little point to note there, although we were looking specifically at dissemination protocols, what I like to call concurrent transmission primitives. So you can actually build up other sorts of protocols from those. So for example, there's one very well known which is called Crystal, and that uses multiple blocks or phases of that flood in order to build up bidirectional data.
And I was wondering, if you want to build on these sensor nodes, they are usually very energy limited. If you want to put this, I mean, when you do a multi-PHY protocol, I see there are two issues. One is it's going to add to the complexity of the device, right? Because you will have to have some kind of way of measuring the interference, making the decision. I mean, having some kind of control loop over the file, which obviously adds some complexity to the device. And I don't know, is that really feasible? Or will it be feasible in some situations? How do you see that?
It's certainly an interesting question. And again, I think this is really what we were pitching the paper at, is for people to use these results to kind of design these sorts of protocols and answer those questions, because you're quite right. That's quite an interesting problem.
Yeah, and the other thing is, if you want to have a multi-PHY, how is your receiver going to know which PHY you are using? Because that's my point. I mean, if you want to change the PHY, you somehow maybe we go back to the first paper and you embed something in something that becomes common to all PHYs. So
I mean, there's actually been some interesting papers. I think there was actually a demo at EWSN this year in Lyon, just before everything shut down. But they were looking, and I think this is TU Graz as well, but they were looking at like a universal preamble. So you send out a universal preamble, and then you can then adapt automatically. And to do that, you would need to be using SDRs rather than commodity hardware that we're using right now.
Yes.
I think there's ways and means to do it, and I think it's a really good, interesting research direction.
That's true. I mean, using SDRs right now, it's perfectly fine. If it does show that it is useful, you will evolve into other hardware, right? But you don't start highly integrated devices while you're still trying, because it's not worth the effort. So yeah, but I thought it was quite interesting. So anybody else have questions? So there's a new line of research opening here on 5 protocols. Yeah, I mean, it's true. So, well, it's 7, it's 6 for me, and also for you, I guess, but 7 for everybody else. So thank you very much for attending the last session of ICNP 2020. And I'm giving now handing over to Sergey Gorinsky.
Yes. Can you hear me? Can you see me?
Yes.
Me then say closing words about the conference. So it's not a conference we try to organize. We wanted to have a conference like Xiaomi organized 7 years ago in Göttingen, when people enjoy the physical aspects of life. But it's not to be, so we had to organize it in the virtual space, and this is a version of a slide you already have seen before. Essentially, we got 78 people attending the workshops on Tuesday, 129 in the main conference. So they overlap 160 registrants altogether, which is an impressive number, I think, for the recent ICNPs I've been. We tried to kind of schedule the program so that there is at least some relevant times, both in Asia and in Americas, where people can join. So the attendance was quite low, I would say. So maybe Anna identified a good reason why is the case, because it's not only the time zone shift, but also people have to do all the other things they can escape from when they go to a physical conference. So I think only during the opening session, we had about 70 people at the peak. and lower numbers at the other times. So if you look at the countries of our attendees, so we had 61 people from US, around 33, 34 from China. Spain was number 3, so we had 10 people from Spain. One person is based in Barcelona who participated online only, and 9 in person here in Madrid, all from India networks. So our Red Pill team was completely local, and we did enjoy the physical aspect of it. So we were hybrid. So it's another picture from the welcome reception. I showed another picture during the opening talk. That's the picture from the different angle looking the Royal Palace, and further down towards the sunset, towards the suburb of Leganés, where the institute is located. In the opening talk, I showed this slide showing the second wave of the coronavirus. And at that time I said, well, things are starting to get better, so maybe some people got regrets not coming here and enjoying it with us. But if you look at a picture of today, so the past week there was another growth in the cases, so maybe it was...
When was the registration deadline?
The registration deadline was...
advanced registration.
Advanced registration was September 22nd, I believe.
October or? No,
September.
no. August?
I think right at the peak.
Huh?
I think right at the peak, September 22nd, I think there was our early registration deadline.
Yeah, okay. I think that's the reason that you didn't get a higher amount of registration as a virtual conference. So by then, you decide to lower down the cost nearly to zero, then you get huge participants.
Yeah. Well, that could be true. So we definitely
we made it for networking conference this year. Entirely very low cost, about $30 or $20 or euros on that cost.
Yeah. Well, I think our cost
also issue tons, hundreds of students traveling grant, so that it's dirty cheap for everybody to participate.
Yeah. Well, actually, the thing is that I don't think cost was a problem. Registration fees were also, I think, quite low, maybe 40 euros for the eligibility member in advance, and slightly more.
No, but considering this is a virtual conference, the registration fee could be dramatically to a marginal, nearly to zero, right?
No, it's true. I think we could have actually we considered in advance to be completely free, but we didn't do it, and I think steering committee didn't really want to go to the have zero cost conference. So despite of us here enjoying a little bit of being physical, we do have money in the bank account. So that's my last slide about coming up. So it's still a plan. So we want to provide souvenirs for everyone and send it by mail. I don't know whether it's going to scale or we'll find power for it, but we're planning to do so. The second item is about live presentation of these QAs, including this particular talk. So we're recording everything, and we're going to put it online and link to the conference website. In fact, we have already a YouTube channel where we have all the presentations up to yesterday published already. So shortly after the conference, we put the other presentations of today online as well, link it to the conference website, and potentially put the slides as well. But for this, we need cooperation from the authors, but for the videos, we're all set. So I think it was pretty much bringing up. So it's nice that Xiaoming is here, because I want to announce an informal general chair award to Xiaoming for his active participation, staying until the end, and being one of the few, if not the only person who was active throughout the conference asking technical questions. So it's quite nice. So I think younger people should learn from their senior colleagues and do the same. So that's pretty much all I wanted to say. So Xiaoming, anybody else wants to comment or ask anything?
Yeah, I think the Q&A could be more lively, given a lot of time was offered afterwards, and people are either not attending, probably not attending the tutorial session about education, how to do the online. I have done that before, therefore I didn't attend that part. But occasionally, I feel people are very unfamiliar with the platform,
yeah,
or they are not willing to speak on the online platform to do the Q&A. So typically, only chairs, session chairs, are taking the. And some session chairs are also not instructed what to do.
yeah.
So it happened.
Well, I think it's learning experience. To me, the surprise was that I've seen many people in the list of registrants. So for them, the fee wasn't a problem, but including the students. And they almost didn't attend at all. So I didn't see them.
Yeah, that's the problem. So I feel that overall, the attendee number in the real sessions are too low. Let's say between 10 to 50, roughly. This range is much lower than a physical conference, which surprised me, because in the early year that I was chairing the networking conference, we have much higher participants, and we encourage people to ask questions, and it would turn out to be more interactive than this one.
Yeah, I think so. Well, again, I don't think it's a registration fee because people paid the fee but didn't show up. I think
as I said, it's true what you said, Sergey, and I was mentioning that when I joined today, which is that I could not, the fact that I am here physically makes it like people don't leave me, you know, they don't let me close the door and say, look, I'm gone for 3 days. And even for teaching, for other things that in a normal conference, they would, you know, have these things that you just, I mean, of course, not every week, but you can postpone and change your teaching so that you can then attend the conferences. You know, with all the meetings, people still expect you to do everything else. So it becomes really impracticable. I think that was, I don't know if for, I think several people.
And also probably there's another community issue that our supervisors or managers needs to teach the students to actively become a member of the community rather than only present their paper and go. So this is a cultural issue. If students don't get instructed in such a way, they feel, okay, I present the work and then I do something else. So they didn't preserve the time for attending the conference and being in as a peer rather than, okay, I present my work and then even in the same session, they disappeared immediately. And they didn't listen to the other talks in the same session. So that's really impolite.
Yeah. Well, I think it's really, I don't know, strange because I've seen some students and advisors pay for them the small fee, but they showed up maybe for 15 minutes during the entire conference.
You know, in one conference which were held in Beijing, I scolded one student because I attended all the poster and demos and asked around why this poster didn't show up. And then that student immediately was called up. I say, if you don't show up, I will inform IEEE to remove you. The main question is that the advisors and the students, they don't take those papers, real presentation and Q&A as the real conference value. They just say, oh, I have a publication. That's the problem.
Yeah, that's true.
So
that's the problem.
In general, the community problem.
Yes, yes, I fully agree. And I think, well, I think it's not really a good explanation, but I think I'm aware at least of 3 other networking related conferences which were going on this week as well. So I don't know if the reason or people doing something else, but there were some other venues to attend. So But surprising to me that it's not only people like Anna who are busy professionals, but even students seem to have a lot to do in life, so that it wasn't the highest.
They're partying before the lockdown.
Maybe. Well, anyway, so it's time for us, for organizing committee, to party a little bit. It was one long year organizing the event. So one way or another, it's finished. And I think there were some quite positives we're taking away. So thank you all for coming and participating. And hopefully there will be better, more physical times again when the ICNP will meet in one place. There will be all the people in the same room and participating and asking questions.
May I ask one more question? It's
Sure.
Not your answer. You are not going to answer it or not, but I just want to point that the accepted paper number is extremely low. Only 30 paper in the whole computer science area. This is one of the smallest conference. So this is not the best practice to encourage people to participate in this community. So I would say, if given 180 submissions, we can go through at least the 40, maybe even 50 papers to encourage more in young blood to enter this kind of wider community in such sense, right? I see the TPCs are serious on their job, but I don't feel for the whole community. If you restricted the acceptance rate as 16% as a healthy situation.
Well, as you very well aware, the selection of technical program is by the EPC chairs.
Yeah, I know. I just wanted to say it's not. You are not going to answer this, but I would like this question to be heard by the steering committee sometime, to push our community to be broadened rather than, okay, we just the best papers, but the others are also not worthwhile.
But I don't think.
But this philosophy needs to be changed.
Yeah. No, I think ICNP steering committee has been pushing over the recent years to have more papers, but I think the specific sets of PC chairs quite often have been much more selective. They worried about the quality and thought that the program is very selective, that it gives more prestige to papers. And I think as a result, it's the outcome. So CCOM this year did very different. 53 papers. So yeah, so I think it's
you need to welcome more open, different kind of angles to be debated in the conference. This is the essence, right?
Yeah, that's well,
if it is a perfect work, then it should be traditionally a journal rather than a conference.
Anyway, so
debate the recent new effort rather than completely solid, no further beta work, right?
Well, Shamin, I think many people will agree with you, so I don't think your opinion is controversial. So I think there are people of the opposite opinion as well. So I think that's why these things are happening, but I don't think we can resolve it here. But it's a good point. It's a good point. So I think it's sometimes you want to have a small paper of highly selective papers, but also you want to have a broader inclusion and more active participation. So definitely having more papers would contribute to that.
Mm-hmm.
Okay, so maybe we can conclude here. And thank you very much.
One more is probably some editorial to help beginners or young students to participate in the academic conference. This kind of tutorial would be still helpful. I don't know whether for each conference to hold such or as a general broadcasting method to do this. But I mean, it's probably not ICNP alone problem. Yeah, okay.
No. Xiaomi,
I'm stopping too many things.
I would like to, what Xiaomi said, I think is very important because I actually only realized quite late, well, actually after finishing my PhD, how you are supposed to be at a conference, right? What's supposed to do, and it's not just going there and presenting and then listening to some things, and and this mentorship is very important. And knowing the SIG Mobile community is now using the sort of binding the travel grants to having some kind of mentorship for the students who actually get the grants. And last year, Rakesh had something very interesting. Sorry, not Rakesh, he's called Rajesh Balakrishnan. He is from Singapore. And he had, like, he organized a session with the students, and he gave them a task, like to attend. So each one could attend, should choose a few sessions, and then go there, the paper, summary of the papers, ask questions, and take notes of the answers so that they engage with the program actually. And also talk to some seniors. He gave them, I mean, there were a few games. He did quite a lot. I mean, you don't have to start with big, right? Because we are all busy people, but there are some activities going that direction. I think that's a very important input from Xiaomi.
Yeah. Well, anyway, so let's conclude here. I think it was much longer than 5 minutes I planned. I think I spent twice as much just to set up my slides. So thank you very much for the inputs, for participating. There are a lot of positives to take away. I like these session shares after actually, I think there was the new faces, and I know many of them have done a great job. So thank you everyone. So let's conclude here and see you at some point later.
Yeah.
Thank you, Sergey, for your effort, great effort making this.
Thank you. Well, I'm learning from you. I still remember your tours of Göttingen, so it's, no, I couldn't reproduce this. So. Anyway, thank you so much. See you.
See you,
everyone. Bye.
Bye, everybody.
Bye.
Thanks to everybody.
Bye. Thanks for all the organization committee.
See you.
Thanks.
See you.